Tina, for this very nice introduction, and also for giving me the possibility to talk about, our work on 2D materials using spectroscopic imaging ellipsometry, even though we are using it, as a characterization tool and to understand the light-matter interaction. However, we are really, experts more on the, let's say, electronic and optical parts and not so much on ellipsometry. So meaning, but, nevertheless, we are really fascinated about, the accuracy of this methodology for our atomically thin materials. Before I get started, let me acknowledge all the people in the group who are really, doing the work, who are doing an excellent job working on the structures, working together with me, producing all the nice data. In particular, here, I would like to thank Alexander Lopian and postdoc in the group, Sebastian Schapen, Pierre-Maurice Piel, Jakob Hens, PhD students who contributed greatly, but also Nikolai, Sven, and Katharina as master students, and Ulrich and Jan Hendrik as bachelor students who also contributed to the data I will present today. And, we run ongoing collaboration with, still with the TU Munich, with the Holländer group. We acknowledge theory support by the Wolfing. We get excellent samples by the SOVA group from Prague, and particularly here, the Robinson group in Penn State, where we get, this 2D polymetals. I will mainly focus today. With Swing Kwek from Singapore, we have a nice collaboration on the theory on those materials. And I also would like to thank the ongoing support from Park Systems, where we still have ongoing work and collaboration with Matthias Huber, but also Peter Thiessen. So from that point of view, what I'm presenting today, really is the work done by all these great peoples. And, I'm just the one presenting it today. The outline very briefly, so meaning, first of all, I would like to introduce 2D materials and the light-matter interaction, which is relevant in the course of this presentation. Then I will show a few showcases on atomically thin semiconductors, just, to give you an idea what we can do with this methodology. And then, is the main focus of today's presentation, temperature-dependent spectroscopic imaging ellipsometry on atomically thin 2D gallium films. So on the left-hand side, you see already one of those films, which is, patterned as the logos of the two universities, and we will go to very low temperatures with those studies. So with that, let's go on to the materials, and let me first get started with the motivations. I mean, why are we interested in 2D materials? You see here, it's really an atomically flat or just a few layer thin material, thickness of less than 1 nanometer typically. But why are we interested in? And maybe you know it already, but let me introduce and start with a citation of Richard Feynman. In his very, let's say, well-known lectures, there's plenty of room at the bottom. He, mentioned, he had a phrase, what could we do with layered structures with just the right layers? What would the properties of materials be if we could arrange the atoms the way we want them? And with these 2D materials, we are very, very close to the statement. And yes, it's really true. We can really do a lot with those structures, and we can achieve phenomena, behavior, which maybe was not, thinkable about before. And actually, let me, just introduce and one aspect into this regard, and one aspect is those 2D materials, and we know many of them. Meanwhile, most of them have the properties that they have just weakly bonded interlayer coupling, bonded by van der Waals interaction. And with that, we don't have dangling bonds. We don't have an registry out of plane. And with that, we can nearly combine them as we would like to do. And, here there was still the analog on with this Lego bridges, but still, those there's a registry, and you can just stack them, in a certain fashion on top of each other. So meaning, meanwhile, it's known we can do much, much more, not only stacking, combining them in an, let's say, arbitrary fashion. We can also rotate the structures. And maybe as you can see here, by this rotation, we get a superimposed highly periodic structure called Marie structure, which also give us a lot of new properties from confined exciton physics towards correlation in minibands. So the magic angle twisted bilayer graphene here in this regard is a very, very prominent example, which depends very much on this Marie wavelength, which is superimposed and which is determined by the twist angle and the mismatch in the lattice constants. I know there's much more into this, and I don't want to focus here. So meaning, even so, we can, stack and twist in arbitrary fashion. We have to consider that also macroscopic reconstructions can occur. However, here we really have a playground to work with these fascinating materials. So actually, what kind of materials do we know and what kind of materials would we like to focus on? So actually known are many, many different ones, starting maybe from the first everything got somehow kicked off in the year 2013, 2014, with graphene, a single sheet of carbon atoms arranged in honeycomb lattice structure. Actually, I guess most of us, have used it already by, just writing with a pencil. We are smearing off this little crystallites. Meanwhile, also a lot of other structures are known, like hexagonal bond nitride, chalcogenides, layer perovskites. Even so, there might be some weak bonding in between the different layers. There are magnets. We have this big group of transition metal dichalcogenides. A lot of them are semiconductors. We have topological insulators, and there's a rather new class, this 2D polymetals, which is, should say, just in half van der Waals materials. So today, I would first briefly, focus on the semiconducting transition metal dichalcogenides, say a little bit about magnetic semiconductors, and then finally focus on these 2D polymetals. And of course, I will introduce them in more detail later on. So actually now we have seen those structures are really interesting. So with that, let's see what we can learn about them and why ellipsometry is useful to let's say, to study the properties. So let's first have a look on an optical micrograph. Here it's an optical micrograph on a so-called molybdenum disulfide flake with some monolayer regions, bilayer region, trilayer, and bulk region. It's a false color representation to a bit enhance the contrast, but I guess we all agree the contrast extremely high, particularly here. If you think about the monolayer, it's just about 6.8 angstrom thick, so less than 1 nanometer. And now my question is, to all of you, why can we see this atomically thin materials by an optical microscope? And actually the question is not why can we see it, but can we see it on any substrates? So meaning, is it independent from the substrate material? Maybe Justina, if you could please start the first poll, it would be excellent.
Yes, it's on.
Thank you. So please participate, yes or no. Can we see it with an optical microscope on any substrate? Okay, I see we have a lot of experts on 2D materials research. So meaning, I would say 3/4, yes, mentioned no, we cannot see it on any substrates. That's absolutely correct. And why? And the relevance, let me continue here. No. Does it work again? Yes. So actually, why we see it, maybe we should get started with that. Why we see it is the so-called reflection contrast. So actually, it's the contrast between the reflected light coming from the bare substrate and from the light coming from the substrate together with the 2D material. And it's also called interference contrast or phase contrast, because what we are considering here, it's really the phase of the reflected light on the different interfaces, which can constructively or deconstructively interfere. And, you can calculate the contrast, meaning the intensity of the reflected light. And here the let's say, normalized to the absolute intensity, it's absolute, let's say, intensity of the reflected light. And from that, we can calculate this wavelength dependent versus, for instance, here, just changing the so-called thickness of the silicon dioxide. So here we're using a substrate silicon dioxide, which is very commonly used. And we change the thickness of the silicon dioxide. And you see there are regions where we have a rather high micro contrast. So sorry, it's the red ones. And the dark blue ones are regions where we have a bare contrast. So meaning, for instance, here, this is 300 or the 150 nanometers, the contrast is really poor. And not only the contrast, but also if you do any optical measurement, PL spectroscopy, Raman, reflectance, we get an extremely poor signal. So meaning we have light guiding effect, and the light is then really trapped within the layer stack and does not come out such that we can observe it. So actually here, you know, that it's really already an insight what we can learn about the material, because the refractive indices of the individual materials, all of them are contributing, and of course the individual thicknesses of the layers, of the thin layers. And now, of course, we are already in our, let's say, focus topic. How can we measure both thickness and the refractive indices of those materials? Well, ellipsometry, spectroscopic ellipsometry is an excellent tool to get access to those properties. And, you know, very briefly, what we measure is the change of the polarization state of the reflected light. So we come in with an arbitrarily, let's say, polarized light, as shown here with the incident beam. That's a plane of incidence and an angle of incidence. And we then measure the change of the polarization of the reflected light. And in the Jones matrix formalism, as here, we can express this, the relative phase shift, by the two, let's say, ellipsometric angles, the psi and the delta, which are then give us exactly those properties. And just as a side note, so meaning here, for the P for the parallel and for the perpendicular, S meaning senkrecht, German senkrecht, polarized light. And the S always confuses me because, you know, I never think about that, you know, in German word enters the international, let's say, language here. But, you know, P for parallel, S for perpendicular. Okay. And, you know, if we have a closer look here, how we can really, you know, express this. So we really span this, let's say, coordinate system. The amplitude ratio is exactly, you know, what we determine, and from that we get then the phase shift. And we can measure this, or we can, let's say, in this phase shift, all refractive indices, all thicknesses of the thin layers, what we measure, and does exactly this calculation. Of course, there might be materials which are not isotropic. There might be materials which are anisotropic, and then we have to consider that the optical constants, even though it's constant, you know, it's not only a function of the wavelengths, it's also, let's say, it's a tensor entity. And equivalently, we can express the refractive indices, or we can also, you know, determine the dielectric tensor to prefer the macroscopic or the microscopic picture. Okay. With that, let us come a bit closer what we're doing. So actually, as mentioned, we measure, in our case, the ellipsometric angles. As I will show in a bit, we then have to fit the measured data to a multi-layer model to get access exactly to the properties we would like to know. So refractive indices and thickness of the individual materials. And with that, we can then, let's say, determine exactly those properties we would like to have. In our case, we use a PCSA geometry, meaning we have a polarizer, compensator, sample analyzer geometry, allowing us to determine the ellipsometric angles. I just would like to mention something also. Miller matrix approach is of course possible. However, typically we don't do it in-house because we don't have a notation stage connected to the cryo state. And when is the matrix approach, let's say, required, particularly if you have an anisotropic material, or if we have depolarizing, let's say, effects, then we have to switch from the Jones matrix to the Stokes formalism, and then, you know, the Miller matrix is, let's say, required. However, today I would really like to focus mainly on, you know, the Jones formalism, where we can really measure, or where it's sufficient to measure delta and psi, the ellipsometric angles. Now, very briefly, let's come to the so-called regression analysis required to extract the parameters we are interested in. So first of all, the flow chart is as follows. We measure the angles, then we construct a model which is as close as possible to the outcome already. So meaning we have to set up all the layers which are included, and we have to assign starting parameters for thickness, maybe roughness, and the optical properties. And of course, the more we already know, the better on ISE modeling. So meaning if you can measure, for instance, one of those elements or one of those, let's say, materials individually, or can get thickness, for instance, at least somehow an estimation from another method like atomic force microscopy. And we have this as an input parameter. Then we compare, the fit to the model. Well, adjust the model and refit until the fit converges. And then at the end of the day, we get the output. And now the question is, how can we construct the models? And here I would like to briefly consider the functions and the physical meaning and relevance which contribute. So in case of metallic films where we have free charge carriers, like electrons, we have mainly two contributions. One contribution is the so-called free electron intraband transitions, meaning if we have here a band, if we have here the Fermi level somehow cutting the band, we can have intraband excitations of charge carriers across the Fermi energy to an higher state, and those contribution to the light-matter interaction is described by the Jude model. But we can also have so-called intraband transitions where we have really an oscillation of the charge density between bands. It's sometimes also called localized plasmon modes, which can be described by a Lorentz oscillator trend. How does the function look like? So the real and imaginary part is plotted here. The dielectric function in this situation. And I would like to draw your attention here to the imaginary part. It's the loss function. You see here this nice Lorentz-like shaped fit, which is exactly the resonance frequency of such kind of oscillation. And here you see the typical Trude behavior for the free electron contribution. So what is changed in case we have semiconductor materials and not metals? Well, actually, we get then not, let's say, free charge carriers, and we don't get this kind of localized plasmon modes. However, we get excitations here across the real band gap shown in a single particle picture. However, in this case, the attraction between, the excited electron holes is such high that we have the formation of so-called excitons, bound electron hole states. And due to the binding energy, the excitonic transitions are reduced from the single particle band gap, and we should change from the single particle picture to an exciton picture, so to a many-body, or in our case, a two-body picture, where we see, according to the hydrogen model of the excitonic states, we have the, let's say, ground state, and then the first excited Rydberg state, second Rydberg state, until we reach the continuum states, actually where, the electron hole pair is infinitely displayed. And, here the energy is identical with the single particle band gap. Those transitions are described as well by Lorentz oscillator terms. And what I should mention in the case of 2D materials, of 2D semiconductors, if we have a dielectric environment to this very 2D layers, you can see the sketch here. Let's say the electric field between the electron hole penetrates surrounding, and due to the reduced screening, together with the reduced dimensionality, the exciton binding energy can be extremely high and up to half an eV or even larger. So meaning this phenomenon is really relevant also at high temperatures, and sometimes like a quarter of the total band gap. Okay, with that, I guess we have the most relevant information. If we let's say, have insulating materials, then Cauchy term Silma functions are, let's say, doing the job. So with that, let's have a look on real data on two-dimensional material. And I would like to get started with an example, which was one of the first done, where we investigated molybdenum disulfide on sapphire substrate. So the history was a little bit that exactly on this substrate, it was hard to determine the structures with an optical microscopy. However, for some other reasons, it was the desired substrate. And from that point of view, we got started with ellipsometry, where first we did an ellipsometric contrast image. So here seeing just intensity ratio between substrate or contrast between substrate and monolayer flake, trilayer, and multilayer part, as we could then confirm also by doing a Raman map. So Raman spectroscopy for those two-dimensional layers is very often sensitive to the number of layers. So we have specific modes with the frequency depending on the number of layers due to interlayer coupling or weak interlayer coupling. What you see here on top is the so-called, let's say, illumination using also a beam cutter, such that we can get rid of backside reflection. So here you see the image knife edge. That's the backside reflection free area, exactly where the flake here is displayed. And here you see an area with backside reflection, which is quite useful, where we would have really trouble, in standard ellipsometry, because if you use this substrate with backside reflections, it would more or less impossible to really get reliable data. But here it was nicely done. So here we could then also, with the imaging option, we could focus, use and reach of interest on the monolayer part, on the trilayer part, and so forth, and measure for each the ellipsometric angles as a function of the light energy. And that then did a modeling. In our case, we did an, let's say, anisotropic approach where we considered the in-plane let's say, axis or in-plane contributions to the tensor as isotropic. However, the out-of-plane tensor anisotropic. And what we could see is the following. So we see here, if you focus on the monolayer, in the loss function, the imaginary part of the dielectric function, that we have this very nice two peaks. And those peaks are well-known A and B axisonic transitions. We see also that we have higher line transitions. If you would look very careful, you see here also let's say, a little edge or a glitch. This is then the single particle transition. But most stunning was that we indeed could also observe some contribution in Z direction, so meaning out of plane, even for the monolayer. There see that's a very tiny contribution, which increase the number of layers, and which is also redshifted as expected with increasing number of layers. Even though I should mention, so meaning if you look for the scale here, we are 2, here we have 40, so meaning, change is, or of course, the in-plane contribution is much, much more than the out-of-plane contribution here. However, still, it's not negligible. And particularly, it can be determined by ellipsometry. Now, that's, having those data for the monolayers, we also wanted to see what's going on if we then start to stack those materials, because we already have seen that stacking gives us a nice way to tune the properties and to go to new functionalities. And here the targeted question was, what happens if we combine those two materials? In our case, it was tungsten diselenide and molybdenum diselenide monolayers. Each of them has a dioic band gap. Each of them is a semiconducting transition metal dichalcogenide. And our question was here, if we combine those materials, does it behave like just two stacked layers on top of each other and, more or less independent from the stacking? Or does here, the combined region somehow form a new type of material which need to be considered and modeled in a, let's say, different way? And that was exactly the result what we then got out of this. The first part here is the real and imaginary part of material 1 of molybdenum disulfide. Here we plot the absorption of the material, so which is predominantly the loss. Here tungsten diselenide monolayer, and also here the loss. And if you combine here the two materials, so here we see again this prominent signatures of the A and B excitons. For this material, tungsten diselenide, we also see one prominent transition at the A exciton. The B exciton would be in this region, where we have also higher lying transitions away from the band gap. Interestingly now, if we have a look for the combined region, the tungsten diselenide, molybdenum diselenide region, we first of all see that the excitonic transitions are redshifted and broadened. That's something we can understand because we change the dielectric environment, and we might have some additional coupling which widens the structure and shortens the lifetime. However, this gray shaded region, that was really something which was stunning to us, because there was no way to model the ellipsometric data in this region here just by assuming that we have two layers stacked on top of each other with slightly, let's say, modified dielectric properties compared to the individual layers. So here we had really to set up a completely new model saying, okay, it's a combined material with a double thickness. Then we could also get a nice description of this part here. And I guess you can see from the view model, it's not just the sum of both materials. It really seems completely different. And, the explanation for that is that while for the slow energetic parts, the orbital contribution to the electronic states are highly confined within each layer. So meaning we have some coupling between the layers, but at the end of the day, it's really just a combination and stack of two materials. In this region, for the higher energetic transitions, we have stronger interlayer coupling and hybridization, such that we really get new kind of states, electronic states, if we combine those two materials. And with that here, we can, in this spectral range, we cannot describe dielectric properties just by, a stack of the individual layers, which was quite, also important for us to understand, for instance, how charge transfer across the junctions, across this, let's say, gap, the heterojunction can occur. Well, with that, let me come to the last example from a semiconductor, and now it's the most recent work. It's I would like to also demonstrate that we can get access to really anisotropic material. Here, a material which is a magnetic semiconductor, chromium sulfur bromide, which is a layered antiferromagnet. You might already see on this optical microscopy image that, the shape here is really, has a high aspect ratio because the crystal is already highly anisotrope. The same is valid for the electronic band structure. The same is valid for the magnetic properties. We have a triaxial magnetic anisotropy, and exactly, what we expect also that we have an anisotropy in the dielectric function. And, it's typically an issue that, for this very thin materials with thicknesses below 10 nanometers, the thickness and the dielectric properties are coupled. So meaning it's really hard to decouple both of them. But with a recent work together with Matthias Suwe from Pack Systems and Sebastian Schaper, we could show that using an, let's say, anisotropic substrate on top, and somehow placing the two materials on top of each other with a mismatch reduces this problem a lot, such that we can also get or that we can decouple the thickness and the optical constances for thicknesses smaller than 10 nanometers. And in our case, we use this approach to get access to the dielectric properties of chromium sulfur bromide. Even though we show here bulk material, we also started very thin layers. We placed it in a rutile substrate, which is highly anisotropic, aligned it off axis. And here, to be honest, due to the anisotropy, we used the Müller matrix approach to get access to the data. And, let's say a very brief sketch how the crystal structure and the setup looks like. So actually, we can also here relate, the substrates such that we can get access to the different axis by the Müller matrix approach. And, that's the sample structure here. You see still we have the crystal structure is this van der Waals materials with a little bit thicker layer structure, still less than 1 nanometer, with chromium, sulfate, and bromide, let's say, atoms arranged in this fashion as shown here. Then let's come to the result. So the result is as follows. Indeed, we can extract the refractive indices and the absorption coefficient for, let's say, this material along the different axes. So just as a reminder, A and B are the two implant axes, and you might see, let's focus here again on the absorption, you see that it really behaves quite different, meaning at the fundamental excitonic transition here, called A, at about 1.25 electron volts, we have more or less only contribution from the A-axis, while we then have a combined contribution here in this higher energy range from 1.55 to about 1.8. And then if you go to even higher energies, then the A-axis is still more prominent. And I guess I got just confused by A and B. Sorry again. So the black trace is the B-axis, which dominates the low energetic part. In the intermediate axis, both of them, and in the higher energetic part, we have the A-axis contributing more. The out-of-plane direction, we have some contributions, but it's not that significant, and we are not, it could be that we have still somehow a mixture due to some surface roughness, which is difficult to really, let's say, separate in this kind of experiments. Well, just to give you the summary, so meaning for this part, we have strong excitonic features along these two directions, and the energetic transitions are in very good agreement with calculations of those transitions. After those more general, let's say, showcases, what we can do with imaging ellipsometry, spectroscopic ellipsometry for very thin materials, isotropic and anisotropic ones, I now would like to come to the temperature-dependent studies. However, I would like maybe to make a short break in case there are some questions already at this stage.
Yes, they are. All right, I can see 3 questions. Let me unmute the first person. Prakash, if you'd like to ask your question to Professor Wurstbauer, you can unmute yourself and have a conversation with us. Otherwise, I can read the question. All right, let me read it loud. How can we identify the monolayer of the material, and what are the limitations of ellipsometry? Is it possible to determine the buckling height of a monolayer?
Hey, that's an excellent question. To be honest, it's difficult, the buckling height to really determine it in with ellipsometry. First of all, it depends a little bit, on the size and the dimension of the buckling. But, if it's a monolayer and you have this very small, tiny perturbations, you might see that there is some roughness. However, then it's difficult, at least in my opinion, to separate it from the, let's say, substrate roughness, what you always have from the roughness then of buckling of the 2D material. I guess you're talking about buckling of graphene, more or less, because the other materials are not that much buckled in my experience. Still, we might have some roughness there. How we can, be sure that we have monolayer versus other layers? Well, we see significant differences. First of all, the electronic properties are changed. For instance, if you look for the semiconductors, for graphene also, if you go to higher energies, there are some differences. And of course, we compared it indeed with other, let's say, methods to be sure, because of this issue with the decoupling, if we, have the right thicknesses.
All right, thank you. Let me unmute the next person, Vinay. Feel free to ask your question. I can see you're unmuted, but we cannot hear you somehow. All right, let me read it aloud for you. I guess we have some technical issues. So the question is, can we use the technique to understand the defect density in thin films having thickness around a micron?
Okay, maybe I can forward this to the experts. I would say it depends a little bit, on the, impact of the defects on the material's properties. If it's an intermixed medium at some point, maybe one can determine the rate of intermixture, but I guess it's hard generally to determine the density, the defect density. But maybe Peter.
Yeah, it's something 1 micrometer is not an issue. We can measure these thin films and also defect densities. It's of course always depending on the details of the system, but in general, 1 micrometer is a very nice area for imaging ellipsometry.
All right, thank you. Maybe let's take one more question. They are coming in all the time. All right, Siddharam. There you go.
Yeah, thank you very much. It's really great presentation. I have the question about this. You use this glass surface and you coated your material. Why you choose the glass and why you select the glass and why you not selected the like mica surface or HOPG surface? Is this thickness is also confirmed by AFM?
Okay. Okay, a lot of questions. So why glass substrate? So meaning we use then the glass substrate, for instance, if you want to cool the material down, then expansion coefficients, also, the optical properties of the glass, and stuff like that, suitable to pattern with contacts, transmission measurements. So those are the, let's say, arguments for certain, let's say, substrate materials. Then the thickness. Well, in our experience, AFM is for this two-dimensional materials, not that accurate as, for instance, ellipsometry and also Raman, because, we measure all dirt, all stuff, if you're not going to ultra-high vacuum. So meaning it's well known also that we always have some, typically if you do it in ambient, we always have some water hard layer on the surface, which is, of course, then also present in this measurement.
Okay, yeah. Thank you, ma'am. Thank you very much. Yeah, thank you. I don't know.
You're welcome. Thank you.
All right. Do we want to proceed or you want to take one more question?
Well, I guess maybe one more quick question, then,
Yeah.
if you such, we can finish.
Yeah, it's indeed very short from Pranab. There you go.
Can you hear me?
Yes, we can hear you.
Yeah. What's the use of the beam cutter?
It's like a shadow. So meaning we can, let's say, shade the part of the backside reflection. So meaning, since we have an angle of incidence, so the light comes in and, goes to the lower surface and comes back. And if we have, somehow shadow in, we can, get rid of, we do not eliminate all the structure, just part of it. And from that part.
Okay.
Was it correctly described somehow?
Okay, thank you.
You're welcome.
Yeah.
All right. So I would suggest to considering the time, I would suggest to proceed with the presentation and we can take the rest of the questions at the end.
Okay, excellent. Okay, then let's continue with atomically thin 2D materials. Actually, it's a rather, let's say, new class materials developed, the synthesis developed by the Robinson Group in Penn State. And what they start is the following. So they use silicon carbide material. They supplement the silicon such that carbon is forming. Then they use plasma to, etch, or let's say some defects inside or some windows. And through these windows, they intercalate elemental metals such as gallium, indium, silver, and stuff like that. And in this process, we get this somehow monobite tri-layer material formed between silicon carbide and the graphene. The graphene is sealing such that we have really let's say protection layer on top. And these elemental metals then formed a structure. They are covalently bonded to the silicon carbide here, particularly to the silicon. And then, among those, they form a metallic-like, let's say, bondings. And then on top to the graphene, it's a van der Waals-like bonding. If we look on the transmission electron microscopy, let's say, analysis, in a cross-sectional geometry, we see, depending on the silicon carbide and the synthesis of the silicon carbide, to get either large step edges or smaller step edges. And, depending also on the terrace sites, however, you always see, here we have this nice intercalated, very well arranged layers of gallium in this example, in this case. And the bile is formed such, as mentioned, one atom is, or let's say the lowest layer is covalently bonded to the silicon, and then the carbon, the next layer sits then either on the carbon side or presumably also here on the hollow side. And they not only can do it with gallium, here an example of a tri-layer, they can do it with indium, they can do it with tin, they can do it with silver. Silver sometimes even forms monolayer. Also here you can see a monolayer part. So actually, there's really variety of different materials that can be intercalated. What is so special about? First of all, 2D gallium turns into a superconductor, and it turns into a superconductor at around 5 to 4 Kelvin, larger than the bulk, let's say at a higher transition temperature as the bulk. That the resistance is not completely vanishing is the reason that we have the step edges. They are covered with graphene, but then we have a network of superconducting patches. If you measure on one single domain, the resistance is really vanishing. Surprisingly, if you go to an alloy indium-gallium mixture, at some point around 50% indium, the system does not longer transition to a superconductor. The resistance drops. However, it doesn't really go to let's say a zero resistance state. That is still somehow unknown why just changing one element and replacing it, the system doesn't longer become a superconductor, even though indium itself as a bulk material would be one. So that's somehow the origin is still unknown. In addition, we have many, let's say, interesting properties. So actually this material shows, let's say, high optical nonlinearity, the second order susceptibilities exceeding those, for instance, of the well-known transition metal like chalcogenides, much larger than, for instance, gold nanoparticles. It's really fully compatible into van der Waals heterostruct, so you can, on top of graphene, can combine it with any other material. It's stable over months and even years, so we remeasure them really a long time. And there are many properties we do not yet understand, like the superconductivity, but also what is their quantum confinement. What is about the linear optical response at low temperatures? Can we tune the properties and the force? And that's exactly the motivation why we started to do ellipsometry on those materials. I guess the concept is clear how we do it. So we're doing, again, this Jones matrix approach, measuring the amplitude ratio and the relative phase shift. In our case, the model, it's simple because, well, it's simple. We have the silicon carbide, it's a semiconductor, however, a wide bandgap semiconductor. So here we're using Cauchy model. Then we have the 2D gallium, and you have the textural graphene, and on top you have typically air or silicon dioxide for the TM analysis, but in our case, we just use the air on top. And with that, graphene is modeled by Mtrude and Tau Lorentz. Gallium indium is by Mtrude plus Tau Lorentz and Lorentz terms, in the silicon carbide by Cauchy term. And with that, we can describe the full structure and can extract the dielectric function of the individual layers. Well, Let's first have a look onto the gallium itself as a bilayer. So those are the measured data. And actually here we changed the angle of incidence to get a few more data sets for the modeling. And you see here not only the data for gallium, we see it immediately also for indium, because we wanted to know, compare it, the properties of those two materials. We can extract the dielectric function. Here we see a very strong localized plasmon contribution at 1.9 eV, which nicely compares to bilayer gallium from theory. So the trilayer would be, due to quantum confinement at lower energy, nicely confirming also the TEM results that we indeed have here on bilayer structure. And actually also here where the error is, we have an so-called epsilon is 0 region, the epsilon 1 turns 0, meaning where, the wavelengths of light is getting infinite. So actually, we cannot do it for gallium. We can also do it for indium. In this case, for indium, we see still localized plasmon. However, we see two peaks here. In the TEM analysis, we see that we have a mixture of bi and trilayer, and that's exactly the reason, or let's say, the fact how we can explain those bilayer structure, because we have contributions from bilayer, which is like a smaller quantum confinement, and from the trilayer, which is due to, again, quantum mechanics redshifted. And from that analysis, we can even extract the contribution of bi and trilayer to be 60 and 40%. So actually, now you know the system, and actually now we would like to cool it. And for the cooling, let me first introduce the setup itself. So meaning you see here already a photograph of the setup. It's, a flipped geometry where the two ellipsometer arms, are parallel to the plane. And here, this little tower here is inside the cold finger with the vacuum can of the cryostat. And, the setup we're using is the EP4 from Park System in a customized fashion. We use 50, 20, 10, and 5 times objective, and we have a spectral range from 450 to 1050 nanometers. We use a subcontinuum white light source for the illumination together with an AOTF filter system. And for the fridge, we use a closed cycle cryostat with an adiabatic demagnetization refrigerator stage. And with that, we can cool the system to about 100 millikelvin in a stable operation. And we have, let's say, windows for direct optical access. And, you see here the geometry. So the top cover is custom made. It's done in our machine shop. Such at the moment, we have fixed windows here and an angle of incidence of 50, or allowing an angle of incidence of 50 degrees. What else? Well, the cold finger is placed on XYZ piezo nanopositioners, because, if we cool the system, thermal expansion causes such that the sample is really moving away from the illumination spot, and such that we can realign the sample. So that's the system. And firsthand, we wanted to check when the windows are open and when we shine light in the system, does we still get low temperatures? And luckily, we have a system where we have superconducting transition at very low temperatures at about 4 Kelvin. And that's exactly the way how we check, that the system is still cold. We measure the resistance. You see here, monitor here the cold finger temperature. And that's exactly here. If you look for the inset, that's where we start the measurement, where the laser is on. And here where we really start the measuring. And then we start to change the wavelength and the polarization. And that's exactly the signals what we see. And what we see here in the resistance is nothing else than an induced photocurrent exactly across the step edges. So therefore we have a slight, let's say, change of the normal part of the sample, not of the superconducting part, meaning the temperature is indeed, below 1 Kelvin. There's another, let's say, little issue what we have to consider, because in one of our very first measurements, you see here the ellipsometric angles versus wavelength, and we saw this peak somehow is not so much related to temperature, it's much more related to measurement time. And then we figured out, okay, we have an ice layer forming on top. And well, maybe due to the interest of time, I suggest that we skip the second poll, and I give immediately the answer. What do you think caused the condensed layer by cooling below 100 Kelvin? Is it water? Is it nitrogen? Is it oxygen? And actually, most likely, is it really nitrogen gas, which are liquefied and condensed together with maybe oxygen, but not so much water, what ice which is forming. Okay, what is the solution? Well, either go to ultra-high vacuum. Second point would be, as we approach it, try that the sample is not at the coldest point at the cold fingers, that you have in close by position, which is cooling faster, like, you know, on cold trap. And that's working nicely. And now, the very last minutes, let me show what we can do with that. So here you see again the ellipsometric angles at room temperature in blue and in yellowish in green of these 2D polymetals. And, you know, I guess it's clearly visible that we have one peak at room temperature versus 2 peaks at low temperatures, which could be due to different interband transitions. Let me show how this structure looks locally. So meaning that's now a psi and delta map at room temperature firsthand. And you see maybe, first of all, here the terraces, which can be nicely visualized, but you might also see that there are some regions which are not intercalated, that we have here some scratches. And that's, you know, are somehow the markers which help us to align, because now if we compare room temperature versus here measurement at 4 Kelvin, we can get the identical structure. It's a bit more blurry because we have some vibrations by the cryocooler, but, you know, still we have a nice imaging option. And if you look very, very carefully, you see that there at low temperatures, we get some contrast on the terraces. So meaning there are some regions which look a little bit brighter than other ones. And if you do the analysis now, for the ellipsometric angle here of psi, you know, versus the function of the photon energy, we see that indeed in those spectra, we see different, let's say, peaks, localized, let's say, yeah, let's call it first peaks. One enlarged region where we, you know, average over, let's say, both substructures, we get exactly both peaks involved. However, also we see here some regions where we indeed see 2 well-separated contributions. And now the big question was, where does those contributions come from? And in our tentative explanation, we can, let's say, explain it by the fact that we have, let's say, a metastable, 2 very energetically close by metastable crystal, let's say, arrangements, where the top layer shifts from the carbon side to the hollow side, as it's displayed here. And at room temperature, we expect due to thermal energy that you know, that the whole structure is in the metastable, let's say, high energetic state. And if we condense it down, depending really on the energetics on the interface, some of the material can really, you know, overcome the energy barrier, and then, you know, sit in the stable, let's say, low temperature phase or the ground state. And other part is still, let's say, sitting on this metastable higher energy states, which would explain the behavior. And, you know, that's now the confirmation of this, let's say, idea. Here at room temperature, we have just one peak for the different regions. If you cool down, now the system starts to display that we have, you know, the separation for the 2 regions, one lower energetic transition, one higher energetic transition. And if we further cool down, this is even more, let's say, clearly visible. And as mentioned, these 2 structures are coming most likely from the arrangement that, you know, in this bilayer system, 2 layer of gallium, the lower part is fixed and the upper part moves slightly from this position on top of the carbon atom to this hollow position. And that's, you know, is the explanation. And of course, the position where the atom sits, you know, impacts very significantly the electronic structure, and with that the interband plasmon contributions, what I explained before. So this peak here is the so-called localized plasmon, where we have a charge density excitation, let's say excited by the light, from one band to a high length and unoccupied band back and forth. And therefore, you know, the band structure here is really dependent on the position of the gallium atoms. With that, you know, I would like to summarize in a nutshell. You know, ellipsometry is really a great tool to not only determine thicknesses, but also really to understand the electronic and optical properties of these very thin materials. In the case of this new class 2D polymetal, it even helps us to identify temperature-dependent changes of the very local registry. And I should mention, this displacement is less than an angstrom. So it's really a very little shift, which can be visualized here and determined by ellipsometry. And with that, I would like to stop here. Thank you very much. And, sorry for being a little bit too long.
Thank you so much, Professor Grusbauer. I think it's still okay. Time-wise. All right, so let's take the rest of the questions. Okay, I will move on with Nia. Nia, you are allowed to talk if you like. Otherwise, I can read it loud for you. All right, so the question is, what are the key criteria to consider when selecting materials for heterostructure stacking?
The desired functionality, I would say. So meaning sometimes you would like them to hybridize, sometimes not. Sometimes you would like to have this Marie flat bands. Maybe sometimes you would like to have more localized zero-dimensional states. Sometimes you don't like to have this Marie effects at all in reconstructions. So it really depends, on the energetics, on the application, what you would like to study.
All right, thank you. Next question is again Siddharam. If you would like to ask it yourself, please feel free to unmute yourself.
Yeah, I already got the answer from the Peter. It's really great to see that at a different temperature. Means you can really see this. Normally we use the TEM analysis. The similar data you get by this spectroscopic ellipsometry. It's a wonderful result. Thank you very much. Where we will get this substrate? My question is about they use the different model to fit the data. Because as Peter, he already said that there is a database is available. So that how can I get those database? Hello?
Yes, there are free, let's say, databases available, ellipsometric databases from different, let's say, sources. In our case, some of is already included in the software provided by Park Systems. So that's actually typically our starting point. But at the end of the day, particularly for these new materials, anyhow, but also for other materials, we then develop them ourselves and check, if it fits to the data. Or to our, let's say, system.
Yeah, great. Thank you, ma'am. Thank you very much.
All right. Thank you. Let's move on to the next question. Just let me unmute the person. Senia, I'm not sure if I'm pronouncing your name right.
Yes.
Yes, we can hear you. Please go ahead.
Thank you very much for your great presentation. I have a question about hybridization. Sorry. I'm wondering how hybridization influence refractive indices for thin materials. So what is the role or major role of hybridization?
If the let's say electronic states hybridize, the energetical structures, the energy dispersion, so the band structure is altered, is changed.
Mm-hmm.
And from that point of view, also the optical properties, particularly those interband transitions, are changed.
Oh, okay, all right. Thank you so much.
All right, thank you. Let's move on to Sala. Oh, there we go. Okay. You are allowed to talk.
Hello?
Yes, we can hear you.
You hear me?
Yes, we can hear you.
Thank you for this nice presentation. And I have a question you about about the phosphorin. What about this? What about the application of this technique for the phosphorin, and how to incorporate this nanomaterials in your materials?
What do you mean with integrate? What material and what materials? Maybe can you please maybe rephrase the last part of the question?
I won't say how to incorporate carbon and other materials in your matrix.
Oh, okay. So meaning how this the synthesis is done. So actually,
Yeah. Thank you.
mentioned, so meaning yeah, we don't do it ourselves, but if I go back to the sketch, it was maybe a bit fast. It's a standard, let's say, growth process of graphene, by sublimation of silicon from silicon carbide. So meaning, the starting point is an hexagonal crystal. It's silicon carbide is a semiconductor used for power electronics. And what's then going on, if you look carefully, by sublimating silicon, there's a graphene layer formed, and typically bilayer or monolayer depending on the parameters. However, you have still this residual bonds here to the substrate, which is a mixture of sp2 and sp3 hybridization. And if you now open up, let's say, some windows to this graphene, then you can intercalate something. It's energetically favorable for this material to go in this interface, and then those remaining bonds are, let's say, released. And gallium likes to bond to the silicon atoms. And the process is stopped again by the energetic of the interface, which can be determined. Well, we do it, but as our collaboration partner do it by the formation of the graphene, but also by the parameters of this intercalation. And if you stop the process, the graphene self-heals, so it closes the defects, and with that you have a perfectly sealed structure with depending on the growth parameters, 1, 2, 3 more layers of the metal underneath.
Thank you. And if you permit me, what do you think if you change the graphene by phosphorin?
Good questions. I guess the concept should be the same, and you can also get later on. You can get rid of the graphene, for instance, by one transfer process. Then of course, you have you should be in somewhere in an inert atmosphere, because otherwise you have an issue with the degradation of the metals.
Thank you. Thank you.
All right. Thank you so much. Let me take one more question from Austin. It's quite long, so it would be nice if you can ask it yourself. Otherwise, I'm happy to read it loud for you. There we go. We can see you are unmuted, Austin. But we cannot hear you. All right, let me read the question. How can instrumentation be optimized to monitor and correct for strain and thermal constraint effects in real time during measurement? That's the first part. Second, what protocols can ensure the preservation of sample surface quality and prevent contamination or phase degradation at low temperatures?
And maybe I start with the second part of the question. It's easier because, here the low temperature help us because it's in a vacuum environment. So meaning, as you know from your fridge, you cannot open it because inside the pressure is lower than the outside. And if you go here to temperatures below, let's say, 77 Kelvin, even nitrogen is liquefied and at some point frozen. So meaning there's nothing else, around which can cause degradation to a sample because it's ultra high vacuum. And I would say the same is then, okay, the second point was stress and strain. Yes, you have to think about thermal expansion coefficients for your materials. In the case of Van der Waals, it's not that crucial because due to the Van der Waals interface, they're sliding. So here it's easy, typically it's hard to somewhat transfer strain to the materials and not the other way around. But of course, also here we have to carefully consider, and yes, strain might be there. There are fingerprints then from other methods like Raman spectroscopy, for instance, so the bonding length, changes the phonon frequencies a lot. At that point of view, you get access to local strain with this kind of method, and then can correlate it again, for instance, to ellipsometric measurements. However, for those materials systems we were investigating here, we didn't face any, let's say, impact of strain during the measurements.